Okay, guys, let's make a run through of this week's or last week's free response problems. So, first of all, this graph tells you a couple of things. First of all, it gives you the amplitude. So, one thing to note on when you're trying to figure out an equation for a graph like this, it's amplitude. Whoops. It's amplitude cosine uh, omega t. That's the formula. It could be cosine or it could be sine. So you just kind of got to look and see whether it's cosine or sine. The indicator is, does it start at 0? If it starts at 0, it's cosine. If it starts at 1, it's sine, because cosine 0, let me make sure I'm not lying to you. Cosine 0 is 1. Wait, no, I'm sorry. It starts at 0, it's sine. If it starts at non-zero number, then it's cosine. All right. So this one starts at 0, so we are going to be working with sine in this case. So we know that VT is going to be equal to A sine omega t. Okay, where omega is the angular frequency. It's basically how fast it's making, how fast it's going back and forth. Um, Omega, if you'll remember, is equal to 2 pi f. All right. So what is this A value? The A value is the amplitude. So it's just this number right here, whatever that is. And I am going to say that it is 0.16. You can say anything between 0.15 and 0.16, but just something that makes sense. To me, it looks like it's at 0.16. So 0.16 sine. And now I need to find out what omega t is. And so I'm going to solve for frequency by finding the period. So the period is from there to there, the time for one complete rotation. And that looks like it's 0.7 seconds. So the period is 0.7 seconds. That means the frequency is 1 over 0.7. And omega would be equal to 2 pi divided by 0.7, because omega is 2 pi f. 2 pi divided by 0.7 is, I believe, 9. Let me make sure I did this correctly. Yeah, 8.97, so we get 9t. And then the final thing that we got to do is we got to say that it's negative. And the reason we say that it's negative is because the initial max is at a negative point. So that means that initially it is negative. All right. So there you go. That's how that works out. All right, give an equation that is the position of x at x equals 0. Given that the initial position is x equals 0, determine the equation x over t. So the deal here is that basically, if we want to find the thing, we got to find the integral of this. So x over xt is equal to the integral of vt. And in this case, it would be the integral of that up there, which would give us xt is equal to 0.16 divided by 9 cosine 9t, I believe. And if you solve for it all the way down, it is equal to 0.018 cosine 9t. There you go. Okay. Let's see. By the way, so on both of these two cases, it says that you get full credit if you have the correct answer, just as something to note. All right, so that takes care of A, and let's go to C. C is calculate the value for K. All right, so this one's a little bit tough because you got to remember some things. But one thing you can do is remember the thing is omega is equal to the square root of square root of K over M, or you can remember that the period is equal to 2 pi square root of M over K. The period's the one I remembered. So we found earlier that the period was 0.7, and so 0.7 is equal to 2 pi square root, and it gave us the mass of the object. The mass of the object was 0.3. So 0.3 over K. You do a little algebra, and you get K is equal to 24.2 newtons per meter. Okay. Whoops. Then for D, we are going to experience some rough friction, some rough surface that's going to cause there to be friction, and we want to, but it's only going to experience it once it gets to the, oh wait, hang on. Okay, yeah. So we want to figure, it's got a rough surface now, and we want to figure out what it is while it's going towards the equilibrium position, and then when it's going away from the equilibrium position. So on both of these, we're going to have a normal force and we're going to have a force of gravity, and we're going to have a normal force and a force of gravity. Those two things are going to be there the entire time. Let's see. Compress the distance d divided by 2. Yeah, so when you get to, when you're approaching the equilibrium position, the force is going to be pushing it to the right, and the friction is going to be pulling it to the left. Okay, spring force. And then once you get to the equilibrium position, now the friction, since it's still moving forward, the friction is going to still be pushing, it's moving forward, so friction is resisting movement, and then the spring force is now acting in the opposite direction because it's crossed that equilibrium point. Now it's pulling the other way. By the way, if you check the answer sheet that I'm sending as well, they have it drawn the opposite way. They sent out a correction to flip that. Okay, so anyway, that's why that doesn't look quite right. Letter E, we want to draw a velocity versus time. You need to be slightly specific on this, so the period should remain the same. So you should have the period at 0.7 seconds each time, and so you should have it crossing 1.4 or 2.1. But since the velocity is decreasing, you need to like have it hit. Let's see. You need to have it hit. Let's call this 0.1 and 0.2 and negative 0.1 and negative 0.2. You need to have it hit somewhere right around its initial position, which was 0.16, and then okay, hang on, trying to get the spots right. There we go. And then you need to have it decreasing over time, and so it doesn't really matter like what your decrease rate is. It just needs to be shown to be decreasing as we move along, but you're still maintaining that that velocity, or sorry, you're still maintaining that period. Okay, so there you go. So basically the period needs to stay the same, but you're just decreasing the velocity of the object, and it needs to approach 0 as you go. Okay, so this next one is the important one. It's also a little bit difficult to explain or to write down, so I'm not going to try to write down everything. I'm just going to try to give you a breakdown of where they had the points and why they had the points for each of those. For question A, basically they didn't care what else you checked as long as you checked the meter stick and the stopwatch. Supposedly, you could do this with just a meter stick and a stopwatch. But if you checked other things, that's great. They give 2 different methods of doing this. I'm going to give the one that I thought of. The way I thought to do this, you're basically asked to outline a procedure for an experiment where you're trying to determine conservation of mechanical energy using transformation from initial potential to translational kinetic. So, like, how would you do this? So first of all, I would use a air track. So I would get an air track with minimal friction, and basically I would set up a situation like this where you have the track and the glider, and you have it running down the track. And so you would measure the height to get mgh. Might need an electronic balance to do that. Oh, sorry, you won't need the mass. And then at the bottom, basically you could measure the distance and the time, and you could figure out the velocity. So for B, the example, they basically say use the electronic balance to determine the mass m, and set the track at an incline, measure the height, place the cart at the top, release it from rest, use the stopwatch to measure the time it takes to move down the incline, measure the distance d it moves down the incline. Okay, so that's one of the tricky things about these questions is you have to stop, and it's hard to remember where to stop. So basically, we're labeling the equipment in our diagram. We would use a scale, air track, put a meter stick in there. You've got the glider, you've got the height, you've got the distance. This is what they want really on this one, with the paragraph explaining what each one of those things are, or like bulleted points explaining what each one of those are. Okay, so then you are tasked with figuring out, like, the next step is to figure out how you're going to use the information from the procedure to tell how you are going to determine whether energy was conserved. So basically, remember, I got h, and I got a distance, and I got a time, and I got a mass. And so I'm trying to figure out how to use that information to calculate the answer. So first of all, I'm going to say that the initial potential energy is equal to mgh, all right? And I'm going to have to find what VF is. So for VF, I've got a distance and a time, but remember it's accelerating, so I don't really know quite what that final velocity would be, but we can assume, since there's no friction, that it's accelerating at a constant rate, which means that d over t should be equal to the average velocity. And since the initial velocity is 0, basically 2d over t should be equal to VF. And so now I have a formula for VF. Kinetic energy is equal to 1/2 mVF squared. And I'm going to find that. So I'm going to find potential energy, find kinetic energy, and if potential energy equals kinetic energy, then mechanical energy is conserved. And so basically, we also should note that the initial potential energy, they want you to note as well that the initial kinetic energy is equal to 0 and the final potential energy is equal to 0. All right, that's actually 1 point each. I would have missed those points just because I don't think to do it, but that was a point they wanted you to mention. And you got 2 points for figuring out the correct instantaneous velocity. Okay. Let's see. Acceleration is constant. Okay, so then for D, after your first trial, your calculations showed that energy increased during the experiment. Assume you made no mathematical errors. Give a reasonable explanation for this. You discovered that you basically, the energy was different than it should have been. The energy was more than it should have been. And you just need to figure out a reasonable cause. So maybe you pushed the glider. Maybe you the height was taller than you measured. There's anything that you can think of that would increase the energy of the system, you could write down. I'm sure there were more, but they said push the glider. I thought maybe you mismeasured the height, but as long as there's a reasonable explanation as to why that would add energy. So pushing the glider would be an added bit of work. Added height would give you some added potential energy. And then on other trials, it shows you decrease the amount of energy. On this one, we could say that there was friction, and you might have had friction involved, providing negative work. You might have had friction's the easiest one to think of on that one. Friction, you could say that the height was shorter than you measured, stuff like that. Okay, and then basically you're just saying that if you had friction, it would take energy away from the system, which would make it seem like it was not being conserved. All right. Okay, so number 3, I apologize. I don't know how on earth I managed to do this, but on your problem set, I flipped them backwards. So the C and D and E came up first. My bad. Uh, okay, so this is a little bit of a tricky one to look at. So basically, on this first part, we're sliding with no friction until we get to point L. When we get to point L, or sorry, get to L, where they start measuring L, we've got this distance L where we are sliding and rotating. And then once we get past there, we're just rotating. Okay? So basically, here we have only a velocity. Here we have a velocity that's lowering and an omega that's increasing to catch up with the velocity. And then here we have a constant velocity and a constant omega. Okay? So this period that we're looking at in red is where basically you hit a rough surface and your object starts spinning, and while omega is catching up to the speed that it's moving forward, while omega is catching up to that speed, the velocity is simultaneously decreasing. And so let's get into this and see if we can figure this out. So we are going to be starting from Newton's second law, and we want to derive a differential equation. So anytime you got a differential equation, you basically just need to have that dv over dt, or d omega over dt, or dx over dt, one of those phrases, okay? So for f equals ma, we want to find a differential equation for the function, the velocity as a function of time. So f equals ma, and then the force that's acting on this is friction, and friction is equal to mu times the normal force, which is mu times mass times 10. And so the force would be equal to mu times mass times 10 equals A. Mass cancels. Oh, I'm sorry. MA. The mass cancels. And basically, A would be mu times 10. And then we want the differential equation, so we're just going to do dv over dt equals mu times 10. And that's all we got to do. Leave it there. Okay? For the angular velocity, we want the torque. So the torque, I don't know why my voice just cracked. The torque would be equal to friction times the radius, capital R, which would be torque is equal to mu times mass times 10 times R. And so torque would be equal to I alpha, and mu times mass times 10 times R is going to be equal to mr squared alpha. And again, we're just solving for alpha first. So mu times 10 divided by R is equal to d omega over dt. And we're just leaving them like that. Okay? So basically because this is equal to alpha. All right? Now, I plugged in 10. They left it in G, but it says that you can do it whatever. I would leave it in G. I'm sorry, I just was going on autopilot there. Okay, so how do you do the rest of this? Well, there's two ways to do it. One is you can actually do the calculus, which is to do dv integrated from 0 to v naught, or rather, sorry, from v to v naught. Dadgummit, I can't do this. From v naught to v is equal to mu times 10 from 0 to t dt, and solve for v using that. So if you do this, you get v minus v naught is equal to mu times 10 t. And let me make sure I did that right. Yeah. And so I'm going to go ahead and just plug this in as G, just so we can not have to worry about it. GT, there we go. And so we end up with V equals V naught plus mu GT. Now, I'm sorry, I left one important thing out. This is negative because it's a friction force, so it's negative. And so this would be a negative term. Okay. Now, you could do this without doing this. You could just do V is equal to V naught plus AT. You know that acceleration is equal to mu times G, so V is equal to V naught minus mu gt. And that's just plugging this in, well, rather this in, and that's perfectly fine. So if you don't know how to do calculus, you don't have to do calculus. Omega works the same way. We could do this with the omegas. The difference is on the omegas is that you start with an omega of 0, so it'd be 0 to omega d omega equals mu times 10 mu g over r 0 to t. And so basically this one just ends up being omega is equal to mu gt over r. But again, you can do omega equals omega naught plus alpha t. Omega is 0, omega naught 0, so you get omega is equal to, plug in the value for alpha here, which is mu g over r times t, and you get the same answer. So it's whatever you want to do. All right, you can do it with calculus or you can do it with algebra. Okay, so this is the C part. So on your thing, you might have to go back up to find this, but C, we want to derive an expression for the time it takes the ring to travel a distance L. All right, so we're trying to figure out how long it takes to travel a distance L, and so basically, when we're at L is when it stops sliding and rolling. So that means that the tangential speed is going to be equal to omega r, because when tangential speed is equal to omega r, you're no longer sliding and rolling. Essentially what that means is that the tangential speed is caught up with the angular speed, or the angular speed is caught up with the linear speed, or the tangential speed, and that's that point where you have equilibrium, where it's like just rolling without sliding. And so we get v is equal to v naught minus mu gt, and we're trying to derive an expression for this. So r omega, we're just going to plug that in over here. You can do omega r omega is equal to v naught minus mu gt, and then we are going to solve for t. And so if I solve for t, okay, so sorry, we got to go back and find that formula for omega from the previous problem. If we look at that omega from the previous problem, we've got r is equal to mu gt over r. Okay, that's the formula for omega from that previous problem, equals v naught minus mu gt. And now we're going to sort like terms and solve for t. So basically the r's cancel here. I've got 2 mu gt equals v naught, or t is equal to v naught over 2 mu g. Okay. So basically this one is just algebra, but you're just having to do two substitutions. You're having to sub in the tangential velocity is equal to omega r, and you're having to sub in omega from the previous formula. All right. For D, we're going to derive an expression for the magnitude of the velocity of immediately after it has traveled the distance L. And so basically we're starting with the same formula, v naught minus mu gt. But we now have an expression for t. So we're going to take this t and plug it in. So v is equal to v naught minus mu g times v naught over 2 mu g. Now notice mu and g cancel conveniently, and we're left with v is equal to v naught minus 1/2 v naught, which is 1/2 v naught, the answer. All right, and then finally, we've got to derive an expression for L. And so with this one, we could do it multiple ways. I just chose to do it this way since I have a value for v naught. I have a value for v in terms of v naught. I did v squared equals v naught squared plus 2al. And so now I can solve it. We know v squared is going to be equal to 1/2 v naught squared. We're just plugging this value in from here. Okay, this is going in here. And then v naught squared, we're going to leave it alone. It's one of the fundamentals. And then plus 2. And then I'm going to do minus mu g, because that's the formula I found for acceleration at the very beginning, L. And now I'm just going to work through this. Okay, so we got 1/4 v naught squared equals v naught squared minus 2 mu g L. I'm solving for L, so I just got to do some rearranging of variables. So I get negative 3/4 V naught equals negative 2 mu GL. The negatives go away. And when I divide that 2 over, I get 3/8 V naught divided by mu G equals L. And so I suppose you could write it a little bit better, like 3/8. There you go. And there's your value for that. Oh, I forgot to square it. There we go. Okay. Whew. All right. So that's the first one. So now let's move on to talk about the second one, the second set. All right. In the second set, we begin by dealing with a spring that's not behaving like a typical spring. So a typical spring would be equal to kx or negative kx, but this spring is doing this. So it's got a different formula that we have to deal with. And so for our expression, we have to do something slightly different as well. So basically, we need to know that the potential energy is the integral from 0 to, usually it's x, f dx, basically. And if you do that with this formula, you end up getting the 1/2 kx squared. That's where that formula comes from. But instead, we're going to do that with the formula from 0 to s in this case for the spring force, which is as squared plus bs, and then we're going to do it with respect to ds, and we're going to solve. And so u ends up being equal to as cubed divided by 3 plus bs squared divided by 2. And then you would obviously have a plus c, but it does give us a area to evaluate it from because, doesn't it? Yes, it does. It says from point, I saw it somewhere. Hang on. Where is it? I lost it. Oh, am I jumping the gun? Is that part B? Yeah, okay. So we leave it like this. There's technically a plus C here. And so, let's see. I think that's all there is to that one. Just double checking to make sure I'm not lying to you. Okay. Oh, I see. So basically what they're saying is if you evaluate it from 0 to s, you don't have to put the plus c on there. All right. So that's the first part. Then for part B, they didn't really give you enough room, but you had enough room underneath A to do this, hopefully. You're going to calculate the speed of the cart immediately after it lost contact with the spring. And so basically, we need to find a formula or we need to just plug in u. We now know the variables, so u is equal to 200 times 0.04 cubed divided by 3 plus 150 times 0.04 squared divided by 2. And if you solve that, you end up getting 0.124 joules. 0.124 joules is going to be equal to the kinetic energy. And so 0.124 would be equal to 1/2 times 0.3 times v squared. I got the 0.3 from right there. And then you solve for v, and v is equal to 0.91 meters per second. So that's part A. Part B, the impulse given to the cart by the spring. So the impulse is going to be equal to, whoops, there we go. J is equal to change in momentum. You could also do like an integral of the force with respect to time. If you wanted to, it just that would probably be more work than it's worth. So for me, what I did was I just did this right here, which would be 0.3 times 0.91. And if you solve for that, you get 0.27. And you need to make sure you put your units on it. And the unit for that would be a Newton second, 0.27 Newton seconds. Okay, and then finally, you're graphing what they show here. So on a graph, clearly label it. First of all, you need to have, whenever you do these, every time y'all do these graphs, make sure you label the axes. That's always a point, if not 2 points. So make sure you label the axes. And when you're doing your spacing, make sure you space it evenly. So 0.2, 0.4, 0.6, 0.8, and 1. And then you start here. I don't know, you can do whatever you want to, but since these are fairly like close together, I'm going to do this up to point. I'm going to go up by 0.4 or 0.25, just like they do there. It makes sense to me. They do give you points for utilizing the whole graph. So if your graph is just like in this segment, they're going to actually take a point away from you. Or not take a point away, but they're not going to give you a point. So like as long as you need to make sure you're using the entire graph. And so this graph ends up looking something like this. All right. Something like this. Yes. No, I did that. Let me see. Something like that. Okay. So you've got a graph that looks like that. I'm sorry, I'm not going to plot all the points for you. Y'all can do that part. I know you can. And so part D, compare the speed of the cart measured by photo gate 1 to the predicted value of the cart just after it loses contact with the spring. List a physical source of error that could account for the difference. So basically, if you say, so we have a predicted value for speed. So our predicted value for speed should be 0.91. Oh, I'm sorry, this is a different one. The kid this time figures out it's 0.32. All right. Notice that there's the car is going way faster than 0.32. So the question is why, and the answer could be the student compressed the spring more than they said they did. They could have had a table that was unlevel, or maybe they didn't have accurate numbers for the actual values on the spring. Could have been any of those things. And so if you had any of those things listed, you got a point for stating that the initial speed is greater than it was predicted to be, and then identifying a source of error. Spring could have been stronger than it said it was. They could have compressed it farther than they said they did. They could have had a sloped table, which gives an added potential energy. From the measured speed, the value of the cart as it rolls down the track give a physical explanation for the reason the speed decreases. The speed could decrease. The easiest thing to say is that it's slowing down because there's friction. Friction could be between the wheels, or it could be between the thing. Could have air resistance. Track isn't perfectly level, and it starts going uphill after a while. All that stuff. All right. Next up. All right. This one was a little bit, I like this one. I thought this was a pretty fun one. So essentially, for A, we need to derive an expression for the height of the ramp, put it in terms of V naught, M, and a fundamental frequency. So basically at point P, we know that it's going at speed V naught. So basically 1/2 M V naught squared is equal to mgh. M's cancel. And if we're solving for h, then basically v naught squared over 2g is equal to h. And so you can solve for that. This formula seems to come up almost every unit. So I've seen that so many times. So I think committing that to memory would be helpful, and either solving it for height or solving it for velocity. For part B, a short time after passing point P, the block is in contact with the wall and moves with a speed v. Is the vertical component of the net force on the block up, down, or 0? And then it's 0 because the normal force and force of gravity are going to cancel out because it's not moving up or down. And so the motion of this one is going to be fundamentally in the direction of the circle. And so, let's see. So basically, you know that since it's moving in a circle, there has to be a force toward the center of the circle. That is going to be provided by the normal force, a horizontal normal force, from the edge of this loop. And they're also going to have friction resisting it. Okay, and so you're going to have a net force this way. Okay, um, so that's the forces acting on it. We have vertical is out of the picture, so what I'm going to do instead is call this the radial direction. This way is going to be radial, and this way is going to be tangential. Okay, so we've got in the radial direction a normal force being provided, or providing the centripetal force to hold in the circle, and in the tangential direction we have a friction force slowing this object down. Okay, for part C, derive an expression for the magnitude of the normal force exerted on the block by a circular wall as a function of V. And so you would have the centripetal force is equal to mv squared over r, and that's really all you have to do. In this case, it's capital R. So mv squared over capital R, that's all that's required. For part D, derive an expression for the magnitude of the tangential acceleration of the block at the instant the block has attained a speed v. So basically, friction is equal to mu times the normal force, okay, which in this case is equal to mu times mv squared over r, okay, and then friction's the only force acting on it, slowing it down, so it's equal to ma. And so if you notice, the m's cancel, and so our acceleration is going to be mu v squared over r. Okay, and then I'm trying to figure out what. Oh, I'm sorry. That's all I got to do there. So that's an expression for the velocity. Or sorry, for the acceleration. So this is the tangential acceleration the object's experiencing here. And then finally, we want to derive an expression v for the block as a function of time. And so here's where our fancy calculus kicks in. And you basically do a dv dt is equal to mu v squared over r. And you swap places, so dv over v squared is equal to mu over r dt, and we're going to integrate this, so integral from v naught to v, sorry, I'm trying to make sure I do it this right, yeah, integral from v naught to v 1 over v squared dv is equal to mu r 0 to t dt. And so if we solve, we get, all right, let me see. So we get v naught 1 over v, is that right? 1 over, trying to make sure, integrating, yes, that's right, negative 1 over v from v naught to v, and then mu r, or mu over rt, and we're evaluating that from 0 to t. So this ends up becoming 1 minus v, or sorry, 1 over v minus 1 v over v naught equals mu t over r. And if we solve for v, you can do some algebra. There's some significant algebra that could be done, or I think you could just say that, I would just say v is equal to mu t over r plus 1 over v naught, and just do that. That works. It's technically right. They reduced it a little bit more. It's up to you. I don't know. It doesn't say there's any specific point for that last final statement. It seems to be that the point is getting the integration right. But anyway, okay, so part 3. Okay, so this one was also fun, I thought. So for A, we're going to derive an expression for the length of time it will take the stone to strike the ice. So height's the only thing that matters there, since he throws it horizontally, so the height. And we can just do, d is equal to 1/2 at squared plus v naught t. Notice that since it's horizontal, that value is 0, and then basically h is equal to 1/2 gt squared. Solve for t, and t would be equal to 2h over g square rooted. And so you got your first answer there. That's just a classic back to the basics formula. For B, assuming that the disc is free to slide on ice, derive an expression for the speed of the disc and the person immediately after the ball is thrown. So the important thing here is linear momentum 1 is equal to linear momentum 2. And so basically before it's 0, and so the kid and the disc are going to be moving one way, and the ball is going to be moving the other way. So mass of the ball, velocity of the ball has got to be added to the mass of the disc plus the mass of the boy times the velocity of both. And you can solve for their momentum, because we know, well, in quotations, we know the mass of the ball and the velocity of the ball. So the mass of the ball is basically 1/20th m times v naught is equal to m plus m over 2 times the velocity that both of them have. And so we end up with 1/20th m v naught equals 3 m over 2 v for both of them. And then we would just solve, m's cancel, divide by 3/2, so we get 1/30th v naught equals the speed for both. So that gives us part B. And then for part C, I'm going to go to a different color. Part C, derive an expression for how long it takes the disc to stop sliding. We know that there is a coefficient of friction mu. It's the only force acting on it, so negative friction is equal to mass times acceleration. Negative mu times mass times 10 is equal to mass times acceleration. Now, the masses, you'll notice, cancel here, so negative mu g is equal to a. And basically, v is equal to v naught plus at, where we know v is going to be 0 because we want it to stop, and v naught is 1/30th. Let's see. So 0 is equal to 1/30th v naught plus, minus mu, it's a terrible mu, minus mu gt. And so we end up with v naught over 30 mu g is equal to t. Okay? Just some algebra with some stuff from the very beginning. All right, final bit is to use, now we got to throw in some, some stuff from our most recent unit. So we got to throw in some angular momentum. We want to derive an expression for the angular speed of the disc immediately after it's thrown. The key here is that same thing is going to be happening here. Angular momentum 1 has got to be equal to angular momentum 2. This one's 0, so 0 has got to be equal to angular momentum 2, which in turn means that the angular momentum of the ball has to be equal to the angular momentum of the other stuff. Okay, so how do we figure out the angular momentum of the ball since it's not necessarily spinning? Well, it's equal to mvr, the mass times the velocity that it's thrown times the radius that it's thrown at. So basically, m, in this case, 1/20th m? So 1/20th m is equal to, v naught r is equal to I total times omega. And that's I total. So I total is going to be the angular momentum of, the moment of inertia for the disk plus the moment of inertia for the boy. All right? And so I total then is equal to mr squared over 2 plus the boy, which would just be mr squared. Let's see. Wait, where was the boy standing? Sorry. Hang on one second. Oh, mr squared for the boy, but the boy is half the mass. So when you add in, so the boy would be just, the boys would be mr squared, but since he's half the mass of the disk, it's 1/2 mr squared. So they have the same thing, so the momentum total is just equal to mr squared. And then you can plug that in. So 1/20th mv naught r squared is equal to mr squared omega. M's cancel, R's cancel, and you are left with, oh, I'm sorry, not all the R's cancel. My bad. Oops. There's no square here. This is just V naught R. There we are. So M's cancel, 1R cancels, and we solve, we get V naught over 20R equals omega. There we go. V naught over 20R. Yeah, so that's it. And then finally, we need to figure out what happens if the boy changes his position. So if the boy changes his position, that's going to change the radius on both the boy and the ball. So for the ball, it's now going to be 1/20th m v naught r over 2, because that's where it's leaving from now. So now it's leaving from right here. It's also going to change up our total momentum here. So instead of it being mr squared divided by 2 plus 1/2 mr squared, because the boy was at the edge, now the boy is at r divided by 2, so that's going to be squared. So we end up with mr squared, 1/2 mr squared plus 1/2 times 1/4 mr squared, which would be 1/8. So 5/8 mr squared is now our I total. So basically, moving this boy changes the total, right? And it also changes what we initially start with. Okay, so it's changing both of them. So now the initial momentum is not 1/20th mv naught r, it's now 1/20th mv naught r over 2, and the total momentum is no longer, or sorry, the total moment of inertia is no longer mr squared, it's now 5/8 mr squared. And we're just going to do the same thing we did before. We're just going to solve for omega. M's cancel, one of the R's cancel, okay, one of the R's cancel, and we're just solving for omega. So we get 1/40th V naught equals 5/8 R omega. All right, and so now we got to solve for this. So 8 V naught over 200 R equals omega. And if we reduce that, we get 1/40th? No, I can't do math. 1/25th R. Yeah. So V naught over 25R is equal to omega. Don't know why I put a square here. Sorry about that. There's a square on this one that I don't know why I put. But anyway. Okay, so let's compare these two, because we're trying to figure out whether the changing that position would make it greater or less than. Just intuitively, you should know it would be less than, because you're bringing that radius in, and since we brought this radius in, since we brought this radius in here, it's going to lower the total amount of momentum available, which means that since they have to cancel each other out, it's going to lower the amount of momentum they would have, which means that it should bring down omega. But you would also notice that the kid moved in, and so we don't know exactly how big of an effect that's going to have, because bringing the kid in would lower the moment of inertia, which makes it easier to spin. So we kind of have to do this little math problem to figure this out. And since these two numbers are different, we know that it's different, so it's not equal. And since the new one is less, It would be less than. Okay, and this is because essentially the bringing the kid in basically lowered the moment of inertia, but it wasn't a direct enough lowering to change the omega or the same way. Okay. All right, so that finishes this up, and go deer.